Have you ever tried to grab a beam of light? Your hand goes right through it, like it's nothing at all. But what if I told you that light, this seemingly weightless thing that passes through your fingers, can become so heavy it could tear a hole in the universe itself? This isn't science fiction. This is a Kugelblitz, and it's one of the most mind-bending possibilities in physics. Think about this. Every second of every day, light from the sun travels 93 million miles just to warm your face. It seems so gentle, so weightless. Yet this same light is secretly carrying enough energy to power our entire planet. When light hits a solar panel, it pushes electrons around to make electricity. When it hits your skin, it has enough force to give you a sunburn. Light might seem weightless, but it's actually pushing on you right now. But here's where things get really strange. Einstein figured out that energy and mass are actually the same thing in different forms. That's what his famous E equals mc squared equation tells us. It means that if you concentrate enough energy in one place, it becomes mass. And if you concentrate enough mass in one place, you get a black hole. So what happens if you concentrate enough light, pure energy, in one tiny space? You get something that shouldn't seem possible, a black hole made entirely of light. The amount of light needed is almost beyond imagination. Remember how I mentioned sunlight? You'd need to capture every single ray of light the sun produces for 89 hours. That's almost 4 straight days of the sun's total output, and squeeze it into a space smaller than an atom. The concentration of energy would be so intense that space itself would buckle under its weight. At this point, something truly bizarre happens. Light, which normally races through space at 186,000 miles per second, would find itself trapped by its own gravitational pull. Imagine throwing a ball so hard it goes all the way around Earth and hits you in the back of the head. That's similar to what happens to light in a Kugelblitz. The light tries to escape, but the gravity from its own energy pulls it back. The forces involved are almost incomprehensible. In that tiny space, energy becomes so concentrated that the rules of physics start to break down. Space becomes so curved that anything crossing a certain boundary, even more light, can never escape. It's like a one-way door in the universe. Things can go in, but nothing comes out. What makes Kugelblitz black holes different from regular black holes is their purity. Normal black holes are made from collapsed stars or other matter, but a Kugelblitz would be made from pure energy. It's the ultimate example of Einstein's E equals mc squared in action. Energy and mass aren't just equivalent, they're the same thing viewed in different ways. The sheer amount of energy needed to create a Kugelblitz reveals something profound about our universe. Let's put this in perspective. If you gathered all the artificial light humans have ever produced throughout history, every light bulb, every campfire, every smartphone screen, and multiplied it by 1 trillion, you still wouldn't have enough energy. Even focusing all the world's most powerful lasers at a single point wouldn't come close. We're talking about concentrating more raw energy than 1 million atomic bombs in a space smaller than a dust particle. But why does light need to be squeezed into such a tiny space? It comes down to gravity's relationship with space itself. When enough energy or mass gathers in one place, it doesn't just create a stronger gravitational pull, it actually warps the fabric of space. Imagine stretching a rubber sheet tight and placing a heavy ball in the middle. The sheet curves downward, creating a well. Now imagine that well becoming so deep that anything that rolls too close to the edge falls in and can't climb back out. That's similar to what happens when light becomes concentrated enough to form a Kugelblitz. The most fascinating part is what happens at the exact moment a Kugelblitz forms. As light spirals inward, trying to escape its own gravitational pull, time itself begins to warp. From an outside perspective, the light appears to slow down as it approaches the point of no return, like a cosmic slow-motion replay. But from the light's perspective, if light could have one, time would flow normally while the rest of the universe appears to speed up. This is the same physics that makes regular black holes so strange, but with a Kugelblitz, it's pure energy, causing these distortions in space and time. Scientists have calculated that if you could somehow create a perfect sphere of light powerful enough to form a Kugelblitz, something even stranger would happen. Just before the black hole forms, the intense concentration of energy would create a kind of mirror effect. The light would begin orbiting itself in increasingly tight circles, creating patterns of unimaginable complexity. It's like trying to watch yourself watching yourself in two parallel mirrors, creating an infinite tunnel of reflections. Except this tunnel would be made of pure energy, twisting both space and time. The energy density at this point becomes so extreme that our current physics equations start to break down. We're pushing into territory where quantum mechanics, the rules of the very small, collides with general relativity, the rules of the very large. This is one reason why Kugelblitz black holes are so important to theoretical physics. They might help us understand how these two fundamental theories fit together. Think about what this means. Light, which we usually think of as the fastest and freest thing in the universe, can become so concentrated that it traps itself. It's like the ultimate cosmic version of trying to run so fast you catch up to yourself. The same force that illuminates our world can, under extreme conditions, create one of the darkest objects possible in the universe. This isn't just a quirk of mathematics. It's a fundamental truth about the nature of energy, mass, and the fabric of reality itself. The existence of Kugelblitz black holes raises profound questions about the early universe. In those first fractions of a second after the Big Bang, the universe was filled with radiation so intense it could have spawned these light-based black holes naturally. The energy density back then was unimaginably high. Every point in space was flooded with more energy than exists in all the stars we can see today. Some scientists think these primordial Kugelblitz black holes might still be out there, invisible remnants from the universe's earliest moments. But these light-forged black holes would behave differently from their matter-based cousins. Since they're made of pure energy, they would evaporate through Hawking radiation much faster than regular black holes. Imagine a cosmic kettle that's constantly boiling away, releasing tiny amounts of energy back into space. The smaller the Kugelblitz, the faster it would evaporate, some disappearing in fractions of a second while releasing more energy than a million supernovas. This rapid evaporation process could have played a crucial role in the early universe. As these light-based black holes evaporated, they would have released their energy back into space, potentially affecting how galaxies and large-scale structures formed. It's like throwing pebbles into a perfectly still pond. The ripples would influence how everything else moves and develops. The implications go even deeper. If we could somehow harness the technology to create and control Kugelblitz black holes, though this is far beyond our current capabilities, they could serve as the ultimate energy storage devices. Unlike regular matter, which can never be completely converted to energy, a Kugelblitz is already pure energy in its most concentrated form. It's nature's perfect battery, though one that would be incredibly dangerous to handle. These light-based black holes also challenge our understanding of information in the universe. When regular matter falls into a black hole, its information, the specific details about what it was and how it was arranged, seems to be lost forever. But what happens to the information contained in light when it becomes so concentrated it traps itself? This question touches on one of the deepest mysteries in physics: whether information can truly be destroyed or if it's always preserved in some form. The study of Kugelblitz black holes might even help us understand the ultimate fate of our universe. As we observe the cosmos expanding and cooling, we might wonder if there's a reverse process. Could concentrated light create new pockets of intense energy and gravity? Could these structures influence how space itself evolves over billions of years? What's particularly fascinating is how Kugelblitz black holes represent a kind of ultimate limit in physics. The point where light, which defines the speed limit of the universe, becomes trapped by its own energy. It's a reminder that even the most fundamental forces and particles in nature can create unexpected phenomena when pushed to extremes. The fact that such objects could theoretically exist shows us that reality is far stranger than we might imagine, operating according to rules that sometimes seem to contradict our everyday experience, but make perfect sense when we dig deeper into the mathematics and physics behind them.